Alrighty, lads and ladies, welcome back to MAC1140 Pre-Calculus. Today, as promised, we are going to talk about exponential functions. We're actually going to move very quickly through the section on exponentials. This is a lightning-paced class, and exponentials and logs are things that you've seen in previous algebra classes. We're really not covering any new content here, so the pace is going to be quite quick. Let me get ready to go with the notes. And we'll dive in. Excuse me, sorry. Okay. Again, the exam went fairly smooth. I appreciate everybody, following instructions, communicating well with me, all of that. That goes a long way. This is MAC1140, which is pre-calc. It's a lecture. And today is the 27th of July. Okay. We're going to finish exponentials, which is really two sections in the book. It's 4.1 and 4.2. And we're going to talk about logarithms. 4.3. Logarithm properties, I think, get their own section here also. Oh, wait, I take back what I said. 4.2 is, natural exponential. 4.3 logarithms. Nah, I was right. And 4.4 is log properties, right? We may not get all the way through 4.4, but yep, that's the roadmap. Anything else I wanted to say? Yeah, as always, if you missed the test, you need to reach out to me immediately. The makeup, let's do this announcement. The makeup for exam 2, if you missed it, is Wednesday, which is tomorrow. In office hours. Remember, starting at 3 p.m. So only if you missed it. But if you missed the test, I would rather you take the makeup than not. We'll worry about the excuse down the road. Just like we said in the syllabus, if for whatever reason you're like unwell or don't have the time or didn't have the time to get yourself there, then I'm happy to let you take the makeup. I'd much rather grade makeups than deal with cheating. So makeup is tomorrow. Anything else like this on your mind? Not really. So we talked about exponential functions. I'll say recall that a function like f of x equals a to the x is a graph looking like one of the two following graphs. Either like this, your horizontal asymptote over here, like 0, y-axis, x-axis, or kind of a horizontal flip version of that. This horizontal asymptote, still y equals 0. Depending on whether a is bigger or smaller than 1. This is if a is larger than 1. This is if a is between 0 and 1. And we talked about why we only ever consider a's which are bigger than 0. A being negative would lead to all sorts of weird things with complex numbers. those are exponentials, right? And all the features of these things that we talked about last time, they're monotonic, either always increasing or always decreasing. They never hit the x-axis, meaning the a to the x is never equal to 0, no matter what you plug in for x. All of those nice properties, features we discussed last Thursday. There is a special exponential. Whose base a is equal to this number e. And e is an irrational number. It's about 2.7182 blah, 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 called the natural exponential. The number e is called Euler's number. Again, that's like 2.7182 blah, 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 is called Euler's number, of the natural base. And there's a bunch of different ways to define the number e. In college algebra, we say that it comes from studying compound interest, where you send the number of compoundings to infinity. The reality of the situation is that the definition of the number e kind of comes from a calculus operation. We want e to the x to be its own derivative, because it turns out all exponential functions have derivatives that are proportional to themselves. So whatever derivative means, e is the special base that makes that thing equal to the original. Euler's number. Euler is a dude, and I know it's spelled like Euler, but I promise it's pronounced Euler because the man was a Swiss-German guy. That's just how they pronounce the EU sound over there, like they call it Europe. Great math joke, by the way. How would Euler have pronounced Euclid? Euclid, maybe. But anyway, Euler's number. Euler is probably the most prolific mathematician of all time. The most important dude ever. He went blind in 1776. I think he was born in like the 1730s, maybe 1740s. Went blind, totally blind in 1776, and still continued just dictating mathematical truths to people who would write them down, proved theorem after theorem after theorem, even though the motherfucker couldn't see. He wasn't writing anything and like, looking at it the way you and I look at mathematics when we want to figure stuff out. It was just clear in his head. There's many things named after him. In fact, today in differential equations, I proved one theorem that is named after Euler, and then we solved a family of differential equations that are also named after Euler. You'll find this guy showing up everywhere in mathematics, and not just in math, but in physics too. I would say Euler is more important than Newton, more important than Gauss, more important than Cauchy. Really just the knees of the bee. So the definition of E is in terms of something called a limit. It's n goes to infinity, 1 plus 1 over n all raised to the nth power. So for example, what does this mean? This means as you put in bigger and bigger and bigger numbers for n, this expression gets closer and closer and closer to that number. So if you take n equal to 1 million, say 1 plus 1 over, or a popular fun thing to do is to put your phone number in for n. I won't do that here, obviously. But I'd be happy to do this calculation for you. Load modifier. So again, the limit notation here, limit as n goes to infinity. It's the same as the end behavior notation that we're using. So I'm saying that this function gets closer and closer and closer to a particular number, or has a horizontal asymptote as n runs off to the right. And we can get a feel for that here. So if I take 1 plus the reciprocal of, or 1 divided by 1 million, and then raise that whole thing to the 1 millionth power, we get, you know, a number that's pretty close to E. The calculators that you'll be using anytime you're doing this sort of stuff will have a button for E, just like they have a button for pi. And it's irrational. So in fact, it's something, a special kind of irrational called transcendental, which means there's no polynomial with integer coefficients that has it as a root, not just irrational, but like super irrational, like pi. Pi is that, 3.14, blah, 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 blah. So we like to use this guy as our base. He makes, because he's about 2.7, he's bigger than 1, his graph looks like this. And the big deal is that his rate of change, if you look over a very small interval, is almost exactly equal to his height. In calculus speak, we would say that the derivative of e to the x is e to the x. So one of the things I'm going to have you be working on in your homework this week is just graphing exponentials, shifted, flipped, stretched, whatever. So let's look at a few of those. So basically, we're adding all functions of the form y equals a to the x to our library of pairing functions. So we can graph lots and lots of other ones as transformations of those, and that's what I aim to do right now. Let's just look at a couple of those. How's about, let's sketch. These are all kind of boring, aren't they? There we go. Sketch g of x equals 2 to the x minus 3, f of x equals 10 to the x plus 3, and h of x equals 1 plus e to the negative x. So 3 functions here, we're going to sketch them. I'll put some practice with like exponent rules and sort of basic arithmetic into your homework because it's important that you are capable of that. But I'm not going to go over that stuff here. That's stuff you've seen in multiple past classes. So 2 to the x minus 3. If I want to graph this, I begin with the graph y equals 2 to the x, which was the first example we looked at last week. We made a table and drew a very nice graph of 2 to the x. He looks like this, right? It's got this horizontal asymptote, y equals 0, goes to the point 0, 1, goes to the point 1, 2, and to the point 2, 4. Let's use those. 2 to the x minus 3 is a transformed version of this. What do I do to this graph to get the graph of g of x?
Go to the right 3.
if the -3 was up here, like x -3, then that would be correct. We'd go to the right, yeah, because like inside stuff is horizontal, outside stuff is vertical. But this guy is down outside of the power, so he's not directly connected to the x. It's like I've taken this whole function, which is this guy, and subtracted 3 on the outside. So what does that do?
Down 3.
Yeah, that moves him down 3. Right? If I add or subtract numbers on the outside, that's a vertical shift. So g of x, I'll draw over here. I'm going to take 2 to the x and shift everything down 3 units. I like to start by drawing in my asymptote. So if I take the line y equals 0 and I shift it down 3 units, it becomes the line y equals -3. And then we'll take a few points. If I take 0, 1 and I shift it down 1, 2, 3, it becomes 0, -2. If I take 1, 2 and shift it down 3, it becomes 1, -1. And if I take 2, 4 and shift it down 3, it becomes 2, 2. Sorry, I drew that as 2, 1. Sorry, 2, 2. I'm going down 3. Oh no, it should be 2, 1. Oh, I'm so sorry. Right the first time. Okay, so our transformed graph is this guy. Still settling down on that horizontal asymptote. We just took 2 to the x and everything down by 3 units. Okay. Is everybody comfy with this? That's our first guy. Now, was it Erica who was thinking left-right shifts?
Yes.
So what would this guy be then, f of x? I'll start with the parent function, y equals 10 to the x. That's the parent for this one. And it's got that same shape as 2 to the x, just slightly different points. He grows a little faster. So here we would have 1, 10. Still down here, 0, 1. And then maybe for my other point, I'll use -1, 1/10. 1/10 is 10 to the -1. So there's that parent function. And then what's the transformation I would do here? This one is a left-right thing, right?
To the left.
Yeah, it's going to be a left shift by 3 units. So will my horizontal asymptote change for this one? I take this picture and move it left 3 units. Yeah, because I'm not going up or down.
Yeah.
Should have done is giving myself a little more space on the left-hand side. So I'll start by drawing in that HA. It's still y equals 0. If I take the point -1, 1/10 and I drag it to the left 3 units, that's going to be -4, 1/10. So I'll go 1, 2, 3, 4. I'll just plop him in right here. It's -4, 1/10. If I take 0, 1 and drag it to the left 3 units, then that's going to become -3, 1. Short on space here. And then 1, 10, if I drag that to the left 3 units, that's going to become -2, 10. So keep my axes similar. And still approaching this asymptote, still having that same basic shape. There it is. This will eventually cross the y-axis. It's just that it's going to be at a huge, huge y value. If you plug in 0 for x here, remember that's always how we find y-intercepts. If you plug in 0 for x, you get 10 to the 3, which is 1,000. So that y-intercept is way up off the page through the back wall of my house. That's just how fast these functions grow. So this is the graph of f of x equals 10 to the x plus 3. So for each of these exponentials, the parent function is just the a to the x, right? Same base raised to the power of x. The e to the x graph, the parent function for this last guy, is one we haven't seen before, but it's the same shape, just differently labeled points. E is bigger than 2 and smaller than 10. So it doesn't grow as fast as this guy. It grows a little bit faster than this guy. It's hard to get that sense of scale in here. I'll do my best. Okay, here's y equals e to the x. 0, 1 is our y-intercept, right? You plug in 0 for x. Anything to the 0 is 1. Here I would have the point 1, e. And please, no decimals, right? If something is a power of e or a multiple of e or something like that, just write e as e. Don't use decimals. And then over here at -1, I have -1, 1 over e. Now the transformations is a little bit more to get to h than there were the other two. What are the two transformations I need to apply to e to the x to get this?
Flip over the y-axis and then up 1.
Very good. So the negative x on the inside, that's a flip over the y-axis or a horizontal flip. And then the +1 that bumps us up 1. So what I'm going to do is draw the sequence of graphs that lead us there. So the horizontal flip, this is going to be the graph y equals e to the -x. It's just going to take this guy and flip it over like this. So now instead of 1, e, I'll have -1, e. 0, 1 stays 0, 1. And 1, 1 over e will be over here. Just taking each of these points and flipping them over. Right through this guy. There it is. All right, and my asymptote hasn't changed at this stage. HA is still y equals 0. And then my very final step would be to bump everything up by 1 unit. So here's the line y equals 1. That's going to serve as my new horizontal asymptote. The point 1, 1 over e is going to get bumped up to 1, 1 over e plus 1, or 1 plus 1 over e. The point 0, 1 goes up to 0, 2. And the point -1, e goes up to -1, 1 plus e. Something like there's the curve. Trust me when I say you need to be super comfortable with exponential functions. Like I said, really the motivation behind the definition for the number e, the motivation for studying exponentials in general is that they behave really nice with respect to calculus operations, differentiation and integration. So you need to know these guys, especially the natural exponentials. I don't think this will be terribly hard. You get those new parent functions comfy in your brain, and then all of this is just the same transformation stuff that we've been doing all semester. So I'm not going to beat you to death with it or anything like that. That's not my intent. I do want to show you one other thing though, and that's how these interact with average rates of change. So any questions on the graphing exercise here? Okay. The average rate of change for, I'll call it f of x equals a to the x, so just a generic exponential function from x to x plus h. It's f of x plus h minus f of x all divided by x plus h minus x, which is h. It's this difference quotient. We saw this earlier. I'm not using a and a plus h because I don't want to confuse with this a. So just say x and x plus h. If I plug in to this recipe, which is the good old fashioned average rate of change recipe, I get a to the x plus h minus a to the x all over h. And then I have an algebra rule that says a to the x plus h, well, that's a to the x times a to the h. So I get this. And what you see is that upstairs, there's sort of two terms. There's this term and there's this term. And common to those two terms is a to the x. So I can factor a to the x out. And what's left is a to the h minus 1 over h. So the average rate of change for an exponential, like a to the x, the average rate of change when you plug in a to the x, simplifies to this. And the big deal is that a to the x shows up again here. So this is a function whose average rate of change is proportional to itself. That's that word proportional from your algebra class is showing up. So the average rate of change for a to the x is that's pretty rare. Remember all those problems where you had to find and simplify the difference quotient for this function or that function? There wasn't a single problem where you got the original function back. Now I'll tell you a little secret. If you send h to 0 in this expression, obviously that's a challenge because you've got an h downstairs here. But if you use the special calculus tool called a limit to let h approach 0 gently, then this piece, if you use e for your base, will get closer and closer to 1. So the instantaneous rate of change, which is what you get as you send h to 0 in this expression, for e to the x is e to the x itself. And that's what it means to say e to the x is its own derivative. But that's a calculus thing. We're not here to spend time on that. I just wanted to show you this algebra because this algebra is kind of what makes exponentials so damn special. They are functions whose growth rate is proportional to their current height. And there's many, many things in the real world that behave like that. Think about how bacteria grow, right? The number of bacteria you're about to have is determined by the number of bacteria you have right now, because they're just dividing. Many populations grow like that. Many other natural phenomena propagate in that way. Epidemics spread like that. Number of sick people you have tomorrow depends on how many sick people you have today. And if each sick person gets 3 other people sick, then the number of sick people tomorrow will be 3 times the number of sick people you have today. So the rate of change is proportional to the function value. That's very special. Okay. Like I said, there will be plenty of problems for you to work in the homework where you get to play with exponential functions. Just kind of trying to come up with what are called function outputs, just playing around with the algebra of the things. And you'll have plenty of chances to graph them also. As always, you need to be graphing these by hand. Not a lot of equation solving here. I'd like to have some equation solving before we get to that. Compound interest stuff, I'm not going to beat you to death with. It's boring as hell. And you won't see any of it in calculus. So this brings us to logarithms. Which is section 4.3. Logarithm functions. Twice so far this semester, you've actually seen the graph of a logarithm function. Once was on your test yesterday. That very last problem about inverses, where you had to draw the graph of f inverse given the graph of f. The graph of f there was an exponential. And the graph that you drew was a logarithm. So I'm just going to define this for you. There's a bunch of ways to define these. It's all about inverses. So definition, the base a logarithm is defined to be the inverse of the base a exponential. Right, all of those exponential graphs that you were looking at are 1-to-1. They all pass the horizontal line test, which means they all have inverses. So in other words, i.e., if f of x is a to the x, then f inverse of x, here's the notation. We write the word log, log, then a little subscript here down below, base a, and then some parentheses of x. This is the base a logarithm of x. Your book and homework will sometimes omit these parentheses. Please don't do that. These parens are so important, so helpful. Without them, things can become very ambiguous. Now, the other way of saying this, as I recall, the definition of inverse function is that, f inverse of f of x should always simplify to x, and the other way around too. F of f inverse of x should simplify to x. Everybody remembers these definitions of inverse function, right? You put on your socks and shoes, you take off your socks and shoes, you get back the thing you fed them, which was your bare feet. In terms of logarithms, and exponentials, This says, well, f inverse, that's the base A logarithm. So log A of f of x, that's a to the x, is equal to x. And f of, so that's a raised to the power of f inverse of x, that's the base A logarithm of x, is also equal to x. All right, so this is like f inverse of f of x. And over here, it's a little bit harder to see. This is f of, and then the here is f inverse of x. So if you take f of, sorry, I bumped it up. If you take f of f inverse of x, you should get x. And if you take f inverse of f of x, you should get x. And these two are usually how people think about exponentials and logarithms when they're using them to solve equations. Now I'll show you what I mean. But before I do that, I'm going to give you one other, it's called characterization. So here's one characterization. Here's the first characterization, which is sort of the standard definition. And then the one that's most useful when you're first meeting these things, because you want to play around with them a little bit. You want something that you can like do stuff with. You can compute some values, make a table, draw a graph, all that. One final characterization. Of logs is the following. If I tell you that the base A logarithm of some number is equal to some other number, that is logically equivalent to saying that A, when raised to that second number, is equal to that first number. So this is sort of three different ways to think about what a logarithm is. They all say the same thing. Each one of these is equivalent to the other. Saying one is the inverse of the other, you say, well, okay, well, I know the definition of inverse function, so if I just plug those specific things in, I get this. And then on the other hand, you've got this here, which says, you know, if y is an output from the base A logarithm associated with the input x, think about inverse functions again, inputs and outputs swap. That means x should be an output from the base A exponential when fed the input y. So three equivalent characterizations. That last one is the most useful when you are first getting to know these things. Okay, so let's do a few quick little examples. Let's compute some logs. Okay, make sure these are all three clear in your notes. Okay, please. I'll hold here just for a second to make sure everybody has time. Okay, so we're gonna find, you know, the base pi log of 1, stuff like that. Compute. How about the base 3 log of 9? The base 5 log of 125. So the base 2 log of 1/2. I said the base pi log of 0, right? Oh, sorry, the base pi log of 1. Let's do that. And what else? Yeah, let's just leave it at this for now. Okay, I want you thinking about this third characterization here. So the base a log of x equals y means a to the y equals x. In other words, this thing is the power to which you must raise a in order to get x. So who can help me out? What is the base 3 logarithm of 9?
Three.
Almost. Remember, we need to be thinking in terms of exponents here, not multiplication. So it's a reasonable guess. I'll tell you that the
2.
log of 27 is 3.
So 2.
Yeah, exactly. This is 2. Why? Because 3 raised to the 2 is equal to 9. So you ask yourself, what power of this would give me the inside? What power of the base gives me the inside? A to what thing gives me x? That is the base a log of x. What's the base 5 log of 125?
3.
3. Why? Because 5 cubed is 125. I want to pause right here because I think this is a good place to try and get comfy before we come down to these two. Any questions about why this first one is 2 or why the second one is 3?
No, but could you state, like, when you say what power?
Yeah, so to find the base a logarithm of x, think of it like this. What power of a gives x? So like what power of 3 gives me 9? What power of 5 gives me 125? Oh, 3 squared is 9. And 5 cubed is 125.
Gotcha.
It's cool stuff, right? I'll show you one of the reasons why this is so important in just a little bit. First, a little more practice. What's the base 2 log of 1/2? What power of 2 gives me 1/2?
-1.
Excellent, -1. Okay. Here's a funny one. What power of pi gives me 1?
0.
Excellent. Pi to the 0 is 1. Anything to the 0 is 1. So the base pi logarithm of 1 is 0. And there's actually nothing special about pi here, right? If this was a 5 or a 3 or a 10 or a 6 or an e, the log of 1, regardless of the base, will always be 0. I want to insert these. This is because 2 to the -1 is 1/2. And this is because pi to the 0 is 1. Okay, so if somebody asks you, just find the log, base whatever of whatever, think of it like this. Some of these are really hard though. Like if I asked you for the base 3 log of 10, I'd be like, oh shit, well, 3 squared is 9, but 3 cubed is 27. 10, what power of 3 gives me 10? I don't fucking know. And indeed, there are the vast majority of logarithms, if you just grab random numbers for this and a random number for this, it's not going to be nice. but I'll justify the existence of such things, that the numbers do exist, I promise you. And then calculators are often going to be the tool used to find them. Really, there's only one logarithm that anyone likes to use. Bring this back. Only one logarithm that anyone likes to use, and it's one of the special ones. These are the base E and base 10 logarithm. Sometimes the base 2 logarithm is considered a special, we call the binary logarithm, but nobody really gives a shit about that. Nobody honestly gives a shit about this one either. It's this one that rules the day. So the base E logarithm, which normally I would write like this, base E log of x. In the calculus sequence, we write that as ln of x, or sometimes with a curly L. It's called the natural log. And there's lots of great jokes about natural and log, right? A log is like a piece of wood. Explore the bad math humor on your own. But yeah, if you're using the base E, which is the natural base, remember Euler's number, the natural base, we call that e to the x the natural exponential. We call the base E logarithm the natural log. And in fact, we use it so much more than anything else, it gets its own notation. It is called ln, logarithm natural, whatever. The other one, the base 10 logarithm, you'll see this written as log of x without anything down there. And this is called the common log. If you want, down the road, if you go on to many, many more math classes, eventually people just write log and they always mean ln. But in this class, I'll be consistent. This is the kind of standard official notation. This is what you'll see throughout the calculus sequence. So the base E log, the natural log, is the one everybody likes to use. I feel like we should get just a little bit of practice with that. Let's do it. Let's compute the ln of E squared, the ln of 1, the ln of E itself, and the ln of 1 over E to the 7. Okay. So remember the question you should be asking yourself. What power of the base gives the inside? So in this first one, what is the base?
E.
E, right? Because ln always means base E. So what power of E gives us E squared?
2.
Yeah, E to the 2 is E to the 2. This doesn't even get a because statement. It's just like a tautology. Oh, sorry. 2. The natural log of E squared is 2. Because E to the 2 is the inside of this, right? All right, what about the natural log of 1? What power of E will give me 1?
0.
0, right? E to the 0 is 1. What power of E will give me E?
1.
1. All right, how about this last one? What power of E will give me 1 over E to the 7?
-7.
Very good, -7. So for all of these, we're doing the exact same thing we did a second ago. I'm asking, what power of E gives the inside? C, doesn't it? E. What power of e gives the inside? So what power of e is e squared? Oh, the second power. What power of e is 1? The 0th power. What power of e is e? The first power. And to what power do I raise e to get 1 over e to the 7? Sorry, yeah, that's -7, right? E to the -7, 1 over e to the 7. So those are your special logarithms, emphasis on the natural one. We could go through this with the common log also, just putting powers of 10 inside, but I don't think that's very exciting. So what I do want to do is look at some graphs, right? There was that graph from the test, but I think it's wise to look at the graphs of 1 or 2 of these. So let's start with the graph of the base 2 logarithm. Graphs, domain, range, logs. Logarithms are going to come with a new domain red flag, right? So we have right now just 2 domain red flags to consider when I ask you what's the domain of this function: any variables under square roots and any variable stuff downstairs in a fraction. For reasons that will become clear in just a moment, if you have variables inside a logarithm, that will also constitute a red flag. I'm going to graph here f of x equals 2 to the x. Again, we know this guy well. This. It's going to be a little bit sketchy to make this look good, but call this 1, call this 2, and call this 4, and this 1 hand. So here is the graph of 2 to the x. Okay, the domain. As with all exponential functions, the domain of 2 to the x is -infinity to infinity. He has this horizontal asymptote over there, but before that, let's write down the range. The range of this function, the one that's graphed here, it never hits the x-axis, right? Never hits 0, never hits the line y equals 0, and it never goes below it. The range here is the open interval from 0 to infinity. It has a horizontal asymptote, and that's the line y equals 0. And the points that I plotted here are 2, 4, 1, 2, 0, 1, and -1, 1/2. So I know that his inverse is the base 2 log of x. So the graph I'm going to draw here is the graph of the base 2 logarithm. And then we'll record its domain and range, and we'll make some observations. All right. The point 0, 1, remember we have this fact, AB is on the graph of f is equivalent to saying BA is on the graph of f inverse, right? Remember that TFAE? That's going to tell me some points I can graph down below. 0, 1 is on the graph of f. So 1, 0 is on the graph of f inverse. 1, 2 is on the graph of f. So 2, 1 is on the graph of f inverse. 2, 4 is on the graph of f. So 1, 2, 3, 4, 2 is on the graph of f inverse. And then what about this guy, -1, 1/2? If I flip that over, that becomes 1/2, -1. So like here's 1/2, here's 1/2, -1. If I take the graph here and I flip everything over the line y equals x, i.e. I swap all the points, I get a graph that looks like this. And indeed, that's the graph of your base 2 logarithm. Something fun, this horizontal asymptote becomes a vertical asymptote. So the logarithms have vertical asymptotes on their graphs. Other fun stuff, domains and ranges switch. The domain of this function, if you smush everything down onto the x-axis, it's the range of the original. And the range of this new function is the domain of the original. Because, you know, all the x points, all the x coordinates from the original are y coordinates on the new one. All the y coordinates on the original are x coordinates on the new one. And you no longer have any horizontal asymptotes, even though this might look like it's kind of evening out, just like this looks like it's a vertical asymptote, it's not. But you do have on the logarithm a vertical asymptote, and it's the line x equals 0. So really just y's and x's swap. That's how inverses work. The ordered pairs here, this is 1/2, -1. This is 1, 0. This is 2, 1. And this is 4, 2. All your log graphs look like this. Just like all your exponential graphs look like that, all your log graphs look like this. And I think it's illustrative to see them both in the same coordinate axis. So the next thing I'm going to do is pull up Desmos. But I want to give you a second, get these nice and clean in your notes, ask any questions you have about where that bottom graph comes from. All right, here comes Desmos. I'm going to start with the line y equals x, and I'm going to put that in dotted. Y equals 2 to the x. That's the graph we started with. And you see, yeah, looks like this. Y equals the base 2 log of x. Looks like that. Now that's what we have here. Some fun facts about logarithms, besides those we've got written there. This green graph looks like it's going to have a horizontal asymptote, doesn't it? It looks like it's sort of settling down, but pick your favorite horizontal line. And if you come out far enough, it will cross any horizontal line eventually. You got to come out real far, but it'll happen. It will, I promise. Here we go. Here we go. Here we go. Oh my goodness. Come on. Come on. All right, come on. Come on. Come on. Come on. Come on. You can do it. You can do it. You can do it. You can do it. There it is. All right. Job done. So you see, in this case, we had to come out about to 1,000. There's a reason for that, because the base 2 logarithm of 1028 is equal to 10, because 2 to the 10 is 1028. So if I wanted to find that exact point, I could. We're going to talk more about that in a minute. But what I really wanted to show you guys here is just the interplay between the two graphs, the exponential in blue and the logarithm in green. They are symmetric about the line y equals x because they are inverses of each other. And that's how we get the graph of the logarithm. You take the graph that you know, the blue one, we got this by plotting points, right? Just making a table. And then you can get the graph of the green one from it, even if you don't know the formula for this function, even if you have no idea what the notation for that function is, because it's defined to be the inverse of the blue function. That's the big deal here. So that's it. That's all we need to get this stuff. Say, I'm going to define this to be the inverse. Why? Why do I need new notation for the inverse of 2 to the x? Why do we call these logarithms? Why not just put a y here and solve for x? Well, because it's fucking impossible. Because you don't have an algebra operation yet that will let you solve y equals 2 to the x for x. And that's where we're going. So remember when I said that a lot of natural phenomena can be modeled by exponential functions? Like I've got some bacteria, and every day each bacterium doubles. Each bacteria splits into 2. Well, then after t days, after x days, I would have 2 to the x bacteria. If I want to know when do I have 50 bacteria, I would need to solve the equation 2 to the x equals 50. And you can't do that using square roots or factoring or any of that stuff. None of that stuff works because the variable is stuck up here in the exponent. So if you wanted to, in general, find the inverse of this function, that means you're going to have to say y equals 2 to the x and then somehow solve that equation for y. There's no way to do that by factoring or taking roots, even taking the xth root of this, which would be a weird operation. Raising both sides to the 1 over x power doesn't work. Doesn't actually save the day. You won't be able to isolate the x. So one of the main utilities of logarithms is that they allow us to solve exponential equations. Lots of other good things too. Myself, I'm a number theorist, and it turns out, fun fact, I'll go ahead and share this with you. Some people like to think about prime numbers a lot. Fun fact, the number of primes less than or equal to x. Like how many primes are there less than 10? How many primes are there less than 1,000,000? Is very close to the ratio x divided by the natural log of x. This is actually a theorem called the prime number theorem. So you see, just one of the many, many ways that logarithms are hugely important in mathematics. This is one of the crowning achievements of modern math. It took hundreds of years to prove this. I won't go into any more of that, but I do want to discuss some other properties of logarithms. So regardless of the base, the following are true. 1, the base a logarithm of 1 will always be 0, no matter what the base is. So the ln of 1, the log of 1, the base 2 log of 1, all of those are 0. Because if you take any of those bases a and raise them to the number 0, you'll always get 1 out. 2. The base a logarithm of a itself is always going to be 1. And then these other two, I wrote them earlier as a characterization, but I'd like to restate them here because, again, they're very important. the base A logarithm of A raised to any power X. Well, to what power must I raise A in order to get A to be X? This is X. And often we see this as an algebra step, saying something like, the rule is that, the base A log of A to the X, you can kind of bring this guy down here, and you get X times the base A log of A, and then the base A log of A is 1, so you just get X. In fact, this sort of thing works great, even if the bases don't match. It's just that at the end, you wouldn't get 1 here. The other one is the other one I said that if you take A and raise it to the power of the base A log of X, you'll get X as well. So, fundamental properties of logarithms. Graphs of different log bases look very similar as long as the bases are bigger than 1. If the base is smaller than 1, then it's going to be a little bit different. So I'll just graph for you one other. About ln of x. You follow the same guiding principles. I'm not going to start with the graph of e to the x, though. I'm going to jump straight to the graph of ln x. I'll call this 1. Should make this about 2. Should make this about e just before 3. And then somewhere way out here, close to 9 would be e squared. So I'm going to go through 1, 0. I'm going to go through e, 1. I'm going to go through e squared, 2. And then within here, if I look at like 1 over e, that would give me negative 1. 1 over e squared would give me negative 2, and so on. So the graph of the natural logarithm looks just like the graph we drew a second ago. Maybe this one needs to come down a little bit. Apologize for my bad art. Big fat points. And again, vertical asymptote here. 0. One other thing, let me add back to your properties of logarithms. 5. The log base a of 0 is always undefined, as is any log base a of any negative number. And that's where that other domain red flag comes from. The inside of logarithms must be positive. We said it earlier. We said the domain of the log is 0 to infinity. Well, that means that you can't plug negatives into logs. You can't plug 0 into logs. So the base a logarithm of 0 is always undefined. So is the base a log of negative 2 or anything like that, right? There is no part of the graph over here where the x's are negative. There's nothing on the left. The ordered pairs that I've chosen here, this was 1 over e, negative 1. This is 1, 0. This is e, 1. This is e squared, 2. So that's the idea. And domain range, all same as before. Okay. You can do all the transformation stuff. You can flip, stretch, rotate. Not rotate, flip, stretch, shift, up, down, left, right, whatever you want. What am I doing for time? Still doing good. Okay, we will get through this. I do want to talk a little bit specifically about finding domains. This graph, one of those super important graphs. In my Calc 1 and Calc 2 classes, I love to, on the first test, give them something that requires them to know this graph, and you'd be shocked how often people don't. Don't be one of those people. Remember the graph of the natural log. So we said earlier that the domain of the logarithm is the open interval 0 to infinity. Finding domains of log functions. You just need the inside to be positive. That's our new red flag. So remember, your first domain red flag is variables under an even root. Your second domain red flag is variables downstairs in a fraction. And now your third and final domain red flag is variables inside a logarithm. So the variables under the square root, you need the inside to be greater than or equal to 0. The variables downstairs, you need the bottom to not be equal to 0. The variables inside the logarithm, you need the inside to be strictly greater than 0. Those are the rules. So if I ask you to find the domain of the function f of x equals the ln of x over x minus 1, you would say, well, I've got this red flag. I need the inside stuff here to be greater than 0. And I also need x minus 1 to not be equal to 0. So here, I would say, okay, by the second red flag, I need x minus 1 to be non-zero, which means x is not allowed to be 1. And then by 3, I need x over x minus 1 to be strictly positive. And this is a rational inequality, which is the sort of inequality we've just been practicing how to solve. How do I solve this inequality?
Set the top and bottom equal to 0.
Very good, very good. Everything's already pulled to one side. There's no factoring to do top and bottom. So we find those special numbers to put on the number line, and they come from making the top and bottom equal to 0. So the top is just x. It is 0 when x is equal to 0. And the bottom is x minus 1. We just learned that x minus 1, the bottom is 0 when x is equal to 1. So those are my two numbers for my number line. That splits me up into 3 regions. Okay, now looking just at the purple thing down here, x over x minus 1, the horizontal asymptote of this guy, just the inside, is 1, which means we're going to be positive over here, and we're going to be positive over here. And then by the multiplicity rule, I know I will be negative in here. Or you could test points. So the domain here, this inequality is solved by the set negative infinity to 0 unioned with 1 to infinity. And I ask, is 1 an element of this set? Is this redundant? And the answer is no, right? It's not. 1 is not included in the set. It's a strict inequality. I wouldn't, I would have to kick it out anyway because it makes the bottom of this piece 0. So your domain is just that. Negative infinity to 0, unioned with 1 to infinity. 1 to infinity. And there will be problems like this on your next test. This is something that will be relevant throughout calculus. You need to be able to find domains of all sorts of functions, logarithms included.
So for the third one, you just set the top and bottom equals 0. That's it.
Well, so remember we say we need the inside of the logarithm to be strictly greater than 0. So what you do with this depends on what the inside of your logarithm is. Here, the inside of my logarithm is this nice rational function. So setting the inside strictly greater than 0 gives me this inequality. And then the way to solve that inequality is by setting the top and bottom equal to 0 and drawing your number line. Yeah.
Got it.
Yep. And so if you're lucky, the inside of your logarithm will be something nice, like a rational function or a polynomial. And polynomial and rational inequalities, that's one of the sections we've just covered. So finding that domain will reduce to one of those. There are other sort of things. I've got a bad joke. What sound, you don't have to write this down, does a drowning number theorist make? Bad joke. Question, answer, log. Because you can compose things inside of logarithms other than rationals or polynomials. I could put a logarithm inside of a logarithm. And then finding the domain would become a little bit trickier because we don't yet know how logarithms interact with inequalities themselves. Although we will discover it. Actually, I'm not sure that's part of this class. Yeah, actually, you guys might not see inequalities. We'll see equations, just equations. Interesting. All right. That joke is so bad, I don't want to end on that. We better keep going. Graphs of logs, finding domains of logs.
I have a question. So for the next test, I have to schedule it in 3 days in advance, not including weekends, so just business days. Do you know when that's going to be?
So our next test is going to be our last midterm. Most likely it'll be on our last day of class. If I remember right, our last day of class is like the 8th, 7th. Yeah, 8th, 7th. So probably the 7th. Okay. I suppose we should move on to the algebra properties of logs. I can give those to you, although we won't have much time to play with them here. And this is 4.4 that we'll be getting into. So we probably won't finish 4.4, but we're going to get in here. The book calls this section laws of logarithms. The basic idea is that each rule for exponents like multiply like bases means adding the exponents. Each one of those has a corresponding rule for logarithms. Rule of law for logarithms. So here are some of those rules, right? You remember that if I take, let's say, a to the x times a to the y, that's the same as a to the x plus y. This is the exponential form. And over here I'll put the log form. Well, the way you would re-express that rule in terms of logarithms is that the base a log of x times y, product on the left, is equal to the sum of base a log of x plus the base a log of y. So one of the things that logs do is they turn multiplication inside into addition outside. And that makes great sense because exponentials turn addition inside into multiplication outside. So these are kind of partner rules. That's the first one. If you divide like bases, a to the x divided by a to the y, then this is the same as a to the x minus y. Those rules for exponents. The logarithm equivalent is that the log, regardless of the base, of a ratio is the log of the top minus the log of the bottom. And then finally, if you take a power and you raise it to a power, we talked about this one last week, that's the same as multiplying the powers. The log version of this looks a little bit funny. It says the base a log of a power is the same as that power times the base a log of the base inside. And this is the one that is a generalization of what I illustrated when we talked about the kind of basic properties of logs a minute ago, that power can come down. So these guys on the right, these are your laws of logarithms. And believe me, there's a lot of ways to get these wrong. I can't tell you how many times I've seen people say like log x divided by log y is the same as log x minus log y. Study these and know them well. The multiplication, division, and powers are happening inside the logs always. And then the addition, subtraction, and multiplication are going on outside. So I don't want to overwhelm. Where are we at? We're a little bit early. I suppose I'll do one or two little examples here, or maybe I'll warn you of the things that are not true. Let's do this. People get things wrong here. Warning. All right. The base a log of a sum of two numbers, like x plus y, is definitely not the sum of the logs. A log of ratios, sorry, a ratio of logs is very much not the same as the log of ratios. And a power of a logarithm, say the y power like way out here, this is not the same as the power being inside. So each of these objects on the right-hand side, these are things that show up somewhere in these. And each of these things on the left-hand side are things that when we look at them, we want to say it's kind of like that, but it's fucking not. It is not. It is not. So don't confuse yourself by saying this is log x minus log y. It's not. This is by this rule. Don't confuse yourself by saying this is log of x times y or log x times log y or anything like that, because it's not. This is the form associated with that. So these are just ways that the notation can be abused. There's more of them. I'm sure I'll see some more creative ones, but the longer I do this, the more ways I see people misuse these. So please be very, very, very careful with your log laws, because it's super possible to mess these up. Anything else? So next time we're going to talk about expanding, combining expressions. We're going to talk about converting equations from like log equations to exponential or exponential to log. We're going to see how to use these things to solve equations. It's these properties, these algebra properties that are so damn nice, that it takes multiplication and splits it up into addition, that it takes powers and turns it into multiplication, kind of reduces the severity of a given expression if you take the logarithm of it. And the magic is, remember that equation we were talking about solving? Y equals 2 to the x, or more generally. So these rules will allow us to solve equations like two to the x equals 3. If you think about it, 2 to the x equals 3 is a pretty weird equation. 2 to the 1 is 2, 2 to the 2 is 4, 3 in there somewhere, but it's not a whole number. And there's no algebra process outside of logarithms that will allow you to solve an equation like this. There's no root you can take, there's no nothing you can factor. Nothing like that at all will work. But I'll tell you right now, this guy, he'll do the job for you. And lots and lots and lots of other things, including calculating inverses of functions that previously we could not calculate inverses for, expanding and simplifying expressions that previously would have taken fucking forever to expand or simplify. Lots of good stuff. So next time we're going to play around with these log properties. We're going to solve some equations, and then we're moving on. So hold on to your pants. This content goes quickly. New homework's going up. I'm going to give you, just like we did last time we had a test, I'm going to give you till Monday to do the new homework, but you want to get on it today. You want to work on it a lot today and tomorrow. Try to have it done by Friday, because there's going to be another new homework coming out Wednesday. Okay, that's it from me, guys. If you need anything, come see me in the office hour. Otherwise, I will see you all tomorrow.